We've done some calculations of forces on charges in some uniform fields, but now we need to do some non-uniform fields. Now, we know when two charges are placed beside one another, they both experience a force depending on their charge. So if they're like charges, they will repel, could have two positives and two negatives, or two negatives. Unlike charges will attract. So some factors that might affect the size of the force, the charge on each charge. That just seems strange to write. The amount of charge on each charge, and the distance between them. Now this formula, if you're paying attention, should look very familiar. This looks almost identical structurally to Newton's law of gravitation. So this is actually known as Coulomb's law, and it states the force between two point charges. Now that's a really important point. It is an important point that we are talking about point charges. So the force equals, we've got a constant K, this is known as Coulomb's constant. We've got the two charges Q1 and Q2, and we are dividing by r squared. So just as a reminder, force due to gravity look like G, M on r squared. Structurally identical, we've got a constant. Instead of charges we had masses, but we've still got the distance between them. Now this constant can actually be broken down a little bit more. We don't often see this, but this constant K is actually equal to 1 on 4 pi times epsilon naught there. Epsilon naught is a strange concept. It's known as the permittivity of free space. I've got the value of it here. I'm sorry about the way this is like sort of gone on to the next line. But we can actually calculate that, but K, I believe, is given in our data booklets for us to actually just use straight away. Lol. And here's our dude Coulomb. So let's actually do some calculations with it. We do need to, I think I skipped over that. The value of K, 9.0 by 10 to the 9, and it's got funny units of Newton meter squared per Coulomb squared. So we are going to have to use that. My apologies, I have just looked it up on the formula sheet, and I have found that the formula sheet's a bit inconsistent because some values are given to 3 sig figs and some are given to 2. So Coulomb's constant is given to 2 sig figs here, so let's update that in our notes. So instead of this, we're going to have 8.99. I'm just going to cross this out so we can have it all together by 10 to the 9 there. So they've given it to 3 sig figs. So let's look at some examples. 2 point charges, each with a charge of 1 Coulomb, are placed 10 millimeters apart. Meters, there we go. Calculate the force experienced by both. So this is going to seem very familiar. So we've got Q1, Q2 on r squared. We're assuming they're point charges, so we don't need to worry about the diameter of a charge or anything like that. And even if it wasn't a point charge, it was a larger one, unless they tell us otherwise, we usually know that they're measuring from the center of the charge. Okay, this new constant, 8.99 by 10 to the, what was it again, 9, times 1 times 1, could have just had 1 squared, it's because we had 2 charges of 1 Coulomb each, and they're 10 millimeters apart. You could have written that as a decimal, I don't mind. Okay, so it was just a bit of index laws with this one. We need to answer it to 2 sig figs though. Oh, actually we need to answer it to 1 sig fig. So that would be 9 by 10 to the 13. Now it's a force, so we still need the units, and that's in newtons. Now, without further calculations, explain what happens to the force on each charge if the charge of 1 is changed to 5 coulombs. Well, the force is proportional to the charge, and let's just say we'll call it Q1. So if Q1 is multiplied by 5, then the force is multiplied by 5. So if we quintuple, if we multiply one of the charges by 5, that means the force needs to multiply by 5 as well because they're directly proportional to each other. Have we explained? I think so, because we said they're directly proportional and then the relationship. Without further calculations, explain what happens to the force on each charge, both of the 1 Coulomb charges. Okay, so they're telling us it's back to 1 Coulomb charge each. If the separation distance is doubled, well, we know the force is proportional to 1 on r squared. Therefore, if r is times by 2, the force will be divided by 4. So we need to quarter the force because it's an inverse square relationship again. Nice. Now, 1 Coulomb is actually a huge amount of charge. If you had 2 charges of this magnitude, the forces between them are big. Like, I don't think I really paused to look at that. 9 by 10 to the 13 newtons is a lot. Oh, excuse me. So we don't tend to deal with whole coulombs. Like micro and milli coulombs are much more likely to be realistic amounts of charge. It is also worth mentioning that electrostatic repulsion is what actually stops mountains from getting squished into the earth due to gravity. There's electrostatic repulsion, the external electrons of the atoms being negatively charged. Well, when you try and smush one atom against another atom, you're trying to smush negatively charged things into each other, and they repel. So even though we've got a literal mountain weighing, I don't even know how much it weighs, millions of kilograms? I don't know if I'm way off or what there. But even though we have that gravitational force acting on those millions of kilograms, the electrostatic repulsion between the atoms stops the atoms from squishing together. I just find that really neat. Gravity is pretty weak in comparison to other forces. Again, it's sort of contextual. Now, we have 2 particles whose charge we've forgotten, but we know that the charge of particle B is twice that of particle A. So I'm going to write QB for the charge on particle B equals, it's twice that of particle A, so 2QA. The force of repulsion between the charges when placed a meter apart, equals 1 meter, is blah, that's our force. What is the charge of each new particle and what might they be? Okay, let's start off with Coulomb's law. Let's, instead of writing Q1 and Q2, let's be clever and write QA and QB here on r squared. You could have written Q1 and Q2 and changed it later. Now, instead of having 2 unknowns, QA and QB, let's perhaps use the fact that we know that QB equals 2 lots of QA. So that changes it to K times QA times, instead of QB, 2QA on r squared. Now, don't do what I frequently have seen people do and write 3QA. That would be 2KQA squared on r squared, because QA times QA gives us QA squared. Now, that was equal to the force. We are actually interested in finding that charge, so let's multiply r squared over both sides. So FR squared, give me 2KQA squared. Double check my working out for me, please. Divide everything by 2k. QA squared is going to be FR squared on 2k, and we need to take the square root. Again, I'm tired, so please double check my working out. If there's something wrong, please discuss it amongst yourselves and correct it. Okay, so the force was 1.84 by 10 to the negative 19. The radius was 1 meter. Oh, forgot the square there. Doesn't matter because it's 1 meter, but it's still important that we put that. And then 2 lots of 8.99 by 10 to the 9. Okay, let's pop it in. Okay, again, please double check my working out here. I don't see anything immediately. I think that 1 meter was written in words. Does that really mean it's 1 sig fig? Ugh, I think it might. So 3 by 10 to the negative 15, and this is a charge, so coulombs. Okay, writing examples can be tough sometimes. Oh, I hear you. Because teachers and examiners need to make sure that an example works, and more importantly, that it makes sense. And I mean makes sense in a physical sense, not just like grammar. So a proton and some theoretical unknown particle are placed 2 meters apart. Ugh, one sig fig again. We've got the proton, and we know Q proton is that elementary charge, which was 1.60. And now I should check. On the formula sheet, is it 1 sig fig or 2? Sorry, 2 or 3, it is 2. So no 0. 1.6 times 10 to the negative 19 coulombs. It's one of those things that you may not have noticed. It's a value that's given in the question, but it's not given in the question. So they tell you it's a proton, but you need to actually look at the formula sheet to know that it's what the charge on it is. Okay, we're told this is the force. What would the charge of the theoretical particle be, and could an examiner put this question on the exam? We'll revisit this bit, and I know I'm likely to forget it because I'm tired, so I'm going to even highlight it. Okay. So let's start off by putting our formula there. I've just written Q1 and Q2 because can't be bothered. So we know the Q proton. Let's maybe call that Q1, and we'll call the unknown Q2. So we need to solve for Q2. So we're going to multiply both sides by r squared, and then we'll divide by kQ1. So Q2 is going to be f r squared on kQ1. Double check that algebra for me, please. Okay, so let's actually substitute values into our equation. 3.6 by 10 to the negative 29, that was that force. The radius was 2, so we've got to square that. K is so strange, some of it's 3 sig figs, 8.99 by 10 to the 9. And Q1 was that charge on a proton, 1.6 by 10 to the negative 19. I know the charge on a proton is positive, but I like to leave any signs out of Coulomb's law. So if we were doing like an electron or a proton, I recommend thinking about putting magnitude signs around this, because you know the direction of the force based on whether they're like charges or unlike charges. Some people get all convoluted putting positives and negatives into Coulomb's law. I think it's unnecessary. Okay, let's calculate. Okay, if you haven't done so, you must practice typing this into your calculator. I'm going to keep forcing you to do it all year. This question was written well for the purpose of being poorly written. I'll tell you what I mean. So, rounding this to 1 sig fig, or even if you round it to 2, you've got 1 by 10 to the negative 19, or 1.0 by 10 to the negative 19. Let's do it to 2 just to really be sure we're illustrating this. And that's coulombs. Now the problem is the elementary charge. We said that was the smallest amount of charge that can exist independently. So because Q2 is less than E, the examiner cannot put this, look at that. Therefore the examiner cannot put this on the exam. It doesn't make any physical sense to have a charge less than that elementary charge, unless we're talking about quarks, but that's different. Okay, to continue to bring this full circle, let's now look at the electric field at a distance from a charge, again in a non-uniform field. To remind us, gravitationally, we used to have F equals G m on r squared. One thing I meant to say about Coulomb's law, some people like to represent it as K, capital Q, lowercase q on r squared. If you wanted to do that, that's fine with me. The letters themselves don't actually matter, it's what they represent. So this is for gravity. And we knew that F equaled little m times G, so that meant If this was G, whatever was multiplied with little m in the equation above was G. So we knew that G was G m on r squared. We could do a similar thing with, instead of G, we've got E, the electric field strength here. So we knew that F equals, I think I might write it the other way just because I think it's cute for this one, on r squared. And we knew that F equaled QE. So that means E equals KQ on R squared. The more I write it, the more I think I like doing the capital Q, lowercase q for Coulomb's law. So, the magnitude of an electric field due to a single point charge at a distance away. So we're talking about, we've got some point charge here. We're putting a little, I don't know, measuring device. Oh, there's that K, 8.99. I don't know why it's over here. Sorry, everyone. But we're measuring the electric field strength at this point here that's far away from this charge. And it's a non-uniform field because a point charge, the field expands out spherically from it. Okay, so E is the electric field strength at that point. Remember, we can measure that in newtons per coulomb. We've also had volts per meter. Q is the charge creating the field. So we're talking about the big charge that's actually creating the field, not a point charge that might be in the larger charge's field. And R is the distance from the charge in meters. And again, K is 8.99 with those fun units. Let's do an example. What is the magnitude and direction of the electric field at a point 30 centimeters left of a point charge? Okay, so we've got a point charge and we've got something that's 30 centimeters to the left. And the point charge is negative. So here's my recommendation. I would use the charge sign to figure out the electric field strength right from the bat. So when we talk about the direction of the electric field, I imagine at the pink cross here, I'm putting that pretend little positive test charge. So it has a negligible self field. It's not changing the field. And I think, which direction would the field point here? Because that's going to be the same direction as the electric field. I thought a spider just crawled across my desk. I'm all good. It's going to be the same as the direction of the electric field here. So if a little point charge was here and there's a negative charge to the right of it, the electric field is going to point right. So I wouldn't bother trying to substitute any negatives or positives into the equation. Use that information at the start and then just substitute in the magnitude. Again, I like to imagine putting magnitude signs around this. Okay, and it was 30 centimeters, so 0.30 meters. So E equals K, capital Q on R squared. K was that 8.99 by 10 to the 9. Q, we were told, I'm just taking the magnitude, 2.0 by 10 to the negative 5. And R, don't forget to square it, 0.30 squared. Don't know why I put that 0.30 in brackets. Oh, doesn't make a difference. Okay, putting this to 2 sig figs, we're going to get 2.0 by 10 to the 6. Now, it is very important to think about what the units of this are. We said we could measure this in newtons per coulomb or volts per meter. In this context, newtons per coulomb probably makes the most sense. It asks us for the magnitude, but we also need the direction. So we do need to point out that it's going to be to the right. Using that convention because they talked about left in the question. So left and right would be appropriate responses here. Okay. This question is vague, so I am going to put a little piece of extra information here. What is the magnitude and direction of the electric field at a point equidistant from 2 protons? And I'm going to say that it needs to be along the line between these 2 protons. So we're going to talk about a point directly between them. As the question is written, you could have a point like here that's equidistant from these 2 protons. but I'm going to narrow the question down and say it needs to be exactly between them. So what do you think the magnitude and direction of a point equidistant between two protons is going to be? Well, you use the technique we spoke about previously. You imagine this one's not there, and which direction would the field be at this point here? So there'd be something pointing in this direction. Again, we're imagining we're putting a little positive test charge there. Then we bring back this charge, get rid of this one. Which direction would the field be due to that right-hand charge? Same size, opposite direction. Pretend those arrows were even mildly the same length or opposite directions. So, therefore, as field from each, charge is equal in magnitude but opposite in direction, field cancels at this point. Nice. Okay, we've got two stationary charges as shown. We've got one that's plus 2q and one that is minus q. So it's half the charge of the other one and the opposite sign. It says at which point is the electric field strength the greatest? Now immediately I'm drawn to points C and B because they are closest to the 2q point. C automatically counteracts D. A is not completely out of the running because we have that negative q we haven't considered yet. Looking at C and B are equidistant from that 2q, but B is also near that minus q. Now at point B it's going to be experiencing the overlapping of two fields. If we just look at 2q at this distance away, it's going to have a big field line, that's not a field line, electric field direction vector pointing to the right for B. If we imagine putting a little positive test charge at that point that's B is labeling, it would be pointing directly away from that plus 2q. Now, if we get rid of that and we now imagine the impact that minus q will have, well, if we put a little positive test charge at that point q, just above, and it's got a charge of negative q, it's going to also experience a field to the right. It's going to be half the size of the arrow that we've already drawn, but it's going to be in the same direction because a little positive test charge there at point B would experience an attraction towards that minus q. So by that logic, we've also cancelled out C as an option. Now A is going to be experiencing two different fields. It will experience a repulsion from the plus 2q, but it's going to be quite small because it's like 1, 2, 3 distance units away. So I don't know, I'll do something like that. It will experience, due to this minus q, it will experience the same size arrow as this blue one we drew here. It doesn't cancel to nothing, but I think we can definitively say that B's got to have the largest electric field strength there.